3.8, implicit differentiation. As opposed to the other sections in this chapter, which are mostly rules for differentiation, either rules for functions in general, the rule applies to every function or every pair of functions, or the other cases where it's been very specific, and you just have a power rule for power functions, a quotient rule for quotient functions, and trigonometric rules for trigonometric functions and things like that. This is a method for taking derivatives for equations. Rather than functions. So most of these, if not all, problems in this section, you're working with non-functions. But even non-functions have derivatives. So for example, very simple case. If you had the unit circle, x squared plus y squared equals 1. So if that's negative 1, and here's 1, and negative 1, so I could draw the unit circle centered at 0. Something like that. Yeah. Okay. So it's certainly not a function, right? Doesn't pass the vertical line test. Right? Consequently, because it does not pass the vertical line test, that means that if I pick any location on here, I'll just pick this location, call it A for a second. And when I map from A to the curve itself, there are two locations, and those two different locations have two different tangent lines. In this case, they're highly related, but in general, they wouldn't have to be. It would depend on what the curve looks like, of course. So already there's a problem that for any location on this curve, except for maybe the endpoints here, every location on this curve, for any x value, you're going to have two y values different from one another. Not only that, the derivatives will be different from one another. So for almost all x here, there are two derivative values. This is not a positive thing at the moment. When trying to calculate derivatives, you'd expect one answer for any x value, and it's not the case for these relations. So we need a way to distinguish between which part of the curve we're on when we're taking derivatives. It will turn out that this method does it almost automatically. Right? But besides that, all the rules that we have so far are designed for function evaluation of derivatives, right? Taking derivatives of functions, and now that this expresses itself, y is not written as a function of x, right? Y of x as a rule is not apparent. It's not explicit. I believe y is a function of x because I know that if I plug a value for x in here right now, like 0, right, then y will be forced to be something, so clearly y depends on x. And if you're thinking, you could easily argue it the other way and say that x is dependent upon y. I would also agree with you that in the case of relations, it's somewhat arbitrary which one you call the independent, which one you call the dependent. And that's why in this case, not only could you take the derivative of y with respect to x, you could also take the derivative of x with respect to y, in these types of situations. It doesn't come up much in the textbook, but it's certainly quite plausible, right? Nevertheless, if we want to treat y as the dependent, we can, because again, we see if we take any particular x value that's legitimate here, and we plug it in, we would have y equaling something specific because we selected an x value. So therefore, y is dependent upon x. But we don't see y of x, right, as a rule explicitly stated. Rather, y is implicitly a function of x through this equation. And that's why this will be called implicit differentiation. Through the rule of the equation.